Okay, this too passed the hour. So good morning, everybody. Thanks for being here for our webinar today, sponsored by VBASE Oil. I am Bob Morzinski, the Director of Professional Development with STLE. This morning, we welcome Dr. Martin Greaves from VBASE Oil and Stephen Eck from VBASE Oil as well. They will be presenting a sponsored webinar this morning on demonstrating efficiency and operational reliability in industrial equipment with secondary polyester-based oils. I'm going to go ahead and hand it over to Dr. Martin Greaves and Stephen Eck right now. I will remind you that if you have a question during the webinar today, please post it to the chat box, which I will utilize in a second to direct you where it's going to be at. Otherwise, I'm going to hand it on over to them for their presentation. Enjoy the presentation. Gentlemen, it's all yours.
Thank you, Robert, and good morning, good afternoon, good evening, everybody, wherever you are in the lubricants world. My name is Martin Greaves, and together with my co-pilot, Stephen Eck, we will be walking you through our VBASE presentation today. We'll start with some very brief introductions. Maybe I'll go first. So as I say, my name is Martin Greaves. I'm the CTO of VBASE Oil Company, and I've been with the company for about 3 years now. I have a degree and PhD in applied chemistry, and I've been in the lubricants industry approximately about 30 years, primarily developing synthetic lubricant-based fluids and indeed formulations derived thereof. I'm currently based in Switzerland, where I'll be presenting the presentation today. Over to Stephen.
Hello, everyone. Stephen Eck here. I'm the COO here at VBASE. I've been with the company for about 9 months, but my entire career, almost 17 years, has been in the lubricants industry, having a variety of roles: engineering by background, chemical engineer, and then operations, supply chain, procurement, business management, corporate development. I've checked just about every box. It's a good ride so far. So happy to be a part of the VBASE team, and really looking forward to getting into this with Martin on how these secondary polyesters can help. Go back to you, Martin, for the agenda.
Yeah, thanks, Stephen. And so the flow of the presentation will be Stephen will introduce the VBASE Oil Company, and then I'll take over and talk about the chemistry and the functionality of secondary polyesters. If you're not familiar with our product line, I'll introduce you to that. And then we'll talk more specifically about the equipment performance of some formulated lubricants that we are developing as part of our, I guess, technology package to help formulators formulate secondary polyester-based products as a base fluid supplier. I'll talk about the efficiency of an environmentally acceptable hydraulic fluid base in our technology, and also the field performance of a hydro-turbine oil that we have developed. And then we'll wrap it up with a Q&A. During the presentation, I will pause at certain points. If you have any questions, as Robert said, put them in the chat, and Stephen and I will be delighted to try and answer those. So pass it over to Stephen to introduce you to the VBASE Oil Company.
Excellent. Thanks, Martin. So yes, the VBASE Oil Company is a company that started in 2021, but the genesis, the technology was a few years prior. The mother company that spun it out is called Tetramer Technologies and is based in Pendleton, South Carolina, right outside of Clemson University. And that's where the commercial and the R&D center are located for VBASE Oil as well. And so the genesis of this was actually a separate program altogether, but the team quickly realized it can be utilized in industrial lubricants as well. And so a lot of the early time was really developing that early value proposition, understanding the technology in the applications, and developing the data to really, on the physical and chemical side of things, to understand it. And so we were able to launch the technology in 2022, starting with the lower viscosity grades, ISO VG 32 to 68. As a startup, we prioritized a lot of the investment dollars into really making this easy to use in the lubricants industry. And so a lot of the monies went into registrations or credentials. And so the early years there, all of these are fully registered from a TSCA and a Canadian DSL perspective in the Western Hemisphere, so from Canada to Argentina, and then also starting to build global profile as well with EU LUSC listing and getting food grade certifications of NSF HX1. The team continued down the line of expanding the technology into the higher viscosity grades. So currently, as of 2024, full commercialization of ISO VG 100 all the way up to 460 as well. And so we feel that this covers a breadth and depth of most industrial applications, but this is a platform technology and has the capability of going on either side of that as well, based on industry needs and problems to solve. In 2025 here, the team's been very, very busy working to expand our addressable market into Europe as well. We are very close on the cusp within weeks of finalizing our EU REACH certification. And Martin and I, along with other colleagues, got to spend some time at the Lube Expo in Germany a couple of weeks ago to continue to spread the message of VBASE and open up an additional market. We do use third-party manufacturing, and that's primarily based in the United States today. We'll go into more detail later in the presentation on that footprint. And then beyond the chemistry and the technology itself, truly the team has a significant amount of molecular design experience, material science experience, and then also, as Martin mentioned, we know this is a new technology. We know in order to take full benefit of the technology, we have to help the industry with the formulation science and how best to utilize these molecules to solve the problems of today and tomorrow. So I'll pass it back over to Martin to go into a little more detail on the chemistry.
Yeah, for those chemists amongst you, we can describe these secondary polyol ester-based fluids as alkoxylated polyol esters more specifically. And if you take a look at the structure on the screen here in front of you, I can describe a little bit more about the functionality of these types of products. If you look at the R1 moiety there, that is simplistically based on an oxygen-rich polyol. The way we make these materials is that we very simplistically take the alkoxylated polyol, and with the secondary hydroxyl groups, we convert them to the synthetic esters. And we can use either oleochemically based or petrochemically derived fatty acids to conduct that esterification. So by building a lot of oxygen in that R1 backbone, we can, for example, improve the thermal management properties. I'll share some data in that area. Improve the detergency, so these molecules have inbuilt detergency, so to speak. And also by building a lot of oxygen into these types of synthetic esters, you can elevate the VI versus classical conventional esters of similar viscosity grades. That R1 group as well is based on a bulky branch polyol that helps with low temperature properties, particularly for the lower viscosity grades. And it also helps as well with helping with hydrolytic stability. The R2 moiety here, we can choose, as I say, the chemically based fatty acids or indeed petrochemically derived fatty acids. That helps with viscosity control, so we can design a whole range of different viscosities based on this technology. It also helps with friction control or traction control, for example. If the fatty acid is saturated and not branched, for example, then we can design products that have a high biodegradability, and also if it's derived from oleochemical feedstocks, to have a high biocarbon content. As Stephen mentioned, this is very versatile chemistry. We can bend the molecules lots of different ways to get the functional performance that you in our industry perhaps need. For those of you not familiar with our product line, I'll kind of walk you through this. You'll notice with regards to the alphanumerics in the nomenclature that we cover, the ISO viscosity range 32 to 68 for the lower viscosity series of products in our line. You'll see that the S grades are saturated and the U grades are unsaturated. Taking a look at some of the typical properties here, you'll see that the VI values range from around about 160 almost up to 200, but they tend to be higher VI values than other types of conventional esters. And perhaps I can give an example. If you look at the VI value of VBASE 32S, it has a VI value around about 162. If you compare that with a similar viscosity grade adipate ester, for example, it's typically around about 20 VI points higher. You'll also see that the low temperature properties are very favorable for this line of products, down to -60 degrees C on the pour point. And if you look a little bit further down the table here, and particularly look at the fire point data, and especially the 5-point data for the VBASE 46U and 68U, you see that their 5 points are north of 320 degrees C. We've had a lot of interest in those products for developing fire-resistant fluids, particularly HFDU fire-resistant hydraulic fluids. Not only are the 5 points quite high for that type of product, but also because these products have a high density of oxygen within their molecular architecture, their heats of combustion are much lower than, for example, petroleum oils and lower than conventional esters that are classically used in this type of application. Looking further down, you'll see that the aniline points are less than minus 10 degrees C. So aniline points are a measure of the polarity of the base fluids. For example, petroleum-based products tend to have aniline points above 100 degrees C. Classical esters typically around about 20 to 30 degrees C. So these products are highly polar base fluids, as reflected in their aniline points. You'll see in green that all these products are readily biodegradable, and they also have a high biocarbon content, again north of 50%. Switching over to our complexes, so these are higher viscosity products. We have products in the range ISO viscosity grade 100 to 460. These products are all saturated products, and again you can see their VI values range from about 185 to 213 for this series. The pour points are higher than the lower viscosity products. That's because these are bigger molecules. And we can correct the pour point if needed by using conventional pour point depressants, such as the polyalkyl methacrylase. 5 points, again, quite high for this series of products. And again, the aniline points, as you see, are around about, are below minus 10 degrees C. Also for this product line, all the products are readily biodegradable and also have a high biocarbon content. I'll just pass it over to Stephen to talk about the environmental and safety performance of these products.
Yeah, absolutely. Thanks, Martin. Yeah, as noted in the last two slides, the conversation really starts with some of the physical and chemical performance benefits of the technology, but depending on what your applications are, we wanted to make sure that they were fully ready to enter any of the markets now and any regulations that may drive into the future. So truly, these molecules were designed to have both performance and green credentials designed for sustainability. So as you mentioned, they're all high content of bio-based materials, all readily biodegradable, including the complex esters all the way up through 460, all non-toxic and non-bioaccumulating. And so all 10 products that you see here are on the LUSC list for the EU and are on the USDA certified bio-based product list. And so depending on where you want to use these molecules, they can go just about anywhere in the application space. And that's part of the simplicity of using the VBASE technology in a wide variety. We understand complexity management and base oil tankage and other things are at a premium. And so we wanted to make sure that one of the fundamental design principles of this technology was ease of use and breadth of market space applications.
So we'll kind of just pause there and just ask if there are any questions on the product chemistry or indeed the product's functionality.
Currently, Martin, there's nothing in the chat.
Okay, great. Let's keep moving then. So we want to transition now to talk about the performance of some formulated products. And just to re-emphasize the point as Stephen made a little bit earlier, we are a base fluid supplier, but in order to drive the growth of these products in the market, we need to develop a lot of knowledge of how to formulate with these products. And of course, we're developing a body of knowledge around formulation science. But not only that, we're also taking it a step further by generating equipment data. So looking at the performance in real equipment and sharing that data with, for example, the team on the call today and, of course, the industry in general. Before I dive into a lot of the equipment performance data, there's really 4 aspects that I want to talk about with regards to functional performance of these products. We truly believe that these can offer better heat management in terms of particularly in terms of their higher volumetric heat capacities. And I'll be sharing a little bit of data in the next couple of slides around that key point. We'll also be talking about improved efficiency or improved productivity when it comes to equipment performance. Stephen talked about these products are safe to use. They can deliver environmental sustainability through their biodegradability and high biocarbon content. And finally, we believe these products can help certainly with equipment reliability. There's many different aspects to that, but because these products have, for example, a lot of oxygen built into the ester architecture, they actually have a lot of inbuilt detergency, for example. And so if you have issues with your petroleum oil, for example, with deposit or varnish formation, these types of products can help solve those types of issues in our industry. So I'll talk a little bit more about these. But I'd like to talk about thermal management. When you look across the industry, there's actually not a lot of published data on the thermal physical properties of base fluids, and indeed formulations based off those. Occasionally you'll see some data based on a specific heat capacity of base oils, but what I feel is very important, and more important than specific heat capacity, is the volumetric heat capacity of base fluids, and indeed formulations derived thereof. Why is that? Simply because when we fill a piece of equipment, we typically fill that equipment by volume and not by mass. So our team earlier on this year has been developing, again, a body of knowledge around base fluids and how our VBASE technology does compare with other base fluids. What you see here on the screen is the volumetric heat capacity of some ISO 46 base fluids. So we've got a group 2, a group 3, a polyalpha olefin, and our VBASE 46S. And you can see that at the 3 temperature measurements that we've chosen to make the measurements at 25, at 50 and 80 degrees C. The group 2 and the group 3 show very similar volumetric heat capacities at those temperatures. The polyalpha olefin somewhat lower than the group 2s and group 3s. But what you can see with the VBASE product, the VBASE 46S, it typically has a volumetric heat capacity at 80 degrees C, somewhere between 9 and 25% higher. So if you're looking to improve the thermal management of your lubricant and your equipment, it may be that the secondary polyester technology is a really good starting point for formulating future generations of fluids. Now, you may be wondering.
Sorry, Martin. Have you my picture? No?
No, I don't think so.
I don't know why, but sorry. I just can I in the end I have a question about the chemistry. I noticed that can I bring out my question here now or not?
Yeah, sure. I'm happy to take it now.
Okay, sorry for interrupt your talking, and I am a question about the turbine oil, and if we formulated the turbine oil, for example, VG32 or 68 or over 100, you know that some crucial factors we have these items is so important for the turbine. For example, cleanliness and emulsibility and foaming characteristic and the other factors like the stability for hydrolytic stability and oxidation and RBOT. You know that in the mineral, or if we formulated the turbine with the mineral or with the group 2 or 3, we have about RBOT about 1,000 minutes. And with this, I don't know how much is over the 1,000 with this base oil. I mean the SPE.
Yeah, let me take that question. So, and I'll be very, very truthful about this because I have to say I don't particularly like the RPVOT test method. It's run at 150 degrees C, and I think in section 4.B of that method, it specifically says, you know, don't compare one product with another, but compare the product versus itself when it ages. I'll share with you some data a little bit later on. I think we've got a product where the RPVOT value is around about 1,240 minutes, if I'm not mistaken. We can fast forward to that in a few minutes. But we found that in turbine applications, we have very good stability at the types of temperatures that this technology would be run at. Yeah.
Yeah, can I have the other one? No. I just have for demonstrability. If you in your text you had some detergency for this type of the base oil, and this detergency I think is maybe cause the messing up the demulsibility for the finished product. What are you thinking about?
Generally, we've seen good demulsibility when we formulate with these products. And again, very, very shortly, I'll share some data on demulsibility of a hydro-turbine. Yeah.
Okay. Sorry.
Okay.
Sorry. I am so sorry for interrupt your talking. Sorry.
Yeah. Thanks for the question. So just for the group, you know, we took a look just a moment ago at the volumetric heat capacities of some hydrocarbon base oils versus the VBASE product. And we saw that the VBASE product did show some significant differences versus the hydrocarbon-based products. You may be wondering how the VBASE product compares with a classical ester, for example. For example, an adipate ester. So if you compare an adipate ester and iso viscosity grade 32 with VBASE 32S, as we've done here, at the three temperatures that I mentioned, then we see that, you know, there's around about a 10% improvement or increase in the volumetric heat capacity. And we think the reason for that is because we built a lot of oxygen into these molecular architectures, which is delivering that higher volumetric heat capacity. So now we go into kind of equipment testing. And I've got to say, you know, we're going to start by talking about the efficiency testing of a hydraulic fluid that we've developed within the team here. The data that I'm going to share with you has been generated by the Milwaukee School of Engineering and particularly by Paul Michael. For those of you that know Paul, he is a world leader in hydraulic fluids and hydraulic fluid testing. We've been working on a program with him through my colleague Zach Hunt, who's in the call now, looking at the whole range of different chemistries and the hydraulic efficiency of those chemistries. And I'd like to share with you a condensed form of all the data that we've generated. And hopefully it sparks some interest. So Paul has a hydraulic dynamometer testing facility that you can see there on the photograph. You know, this is based on a radial piston motor, an axial piston pump, 100-liter reservoir, fluid reservoir, and he's conducted testing of a range of different fluids at 50 degrees C and 80 degrees C. The data that I'm going to share with you today is simply based on 80 degrees C. There is a huge amount of data that's been generated as part of this program. The goal of the program was, as I say, to look at the effect of fluid selection on hydraulic system efficiency. The data I'm going to share with you now simply compares two fluids, the VBASE technology versus a leading petroleum-based brand hydraulic fluid. If you're in the hydraulic fluids world, you would know this type of product. What Paul and his team have done in terms of making measurements on the dynamometer is they've focused on two aspects, the motor torque loss. So this is the estimated power losses due to friction. We know that lower motor torque loss translates into higher work output. What does that mean practically? It means that, if you've got an excavator, then you can fill a bucket faster or maybe even push a load further. He's also looked at system flow losses. I'll show some data on that. So this is an estimation of the power losses due to leakage or compression, for example. We know as well that lower system flow losses translate into lower power input. What does that mean from a practical point of view? It means that you can swing a boom of an excavator or make a turn quicker and so on. The industry, our industry often talks about increased efficiency, but really at the end user, I think it's fair to say that they're more concerned about the increased productivity that they can derive from that increased efficiency. So as part of this work, we're looking at designing lubricants that can increase the work output and reduce the power input. The two fluids that we're going to talk about in the next few slides, as I mentioned, is a petroleum-based hydraulic fluid. It is an industry leader compared with our VBASE technology. And what I want to do here is I want to compare some of the key points of these fluids. You'll see that for the industrial hydraulic fluid, it has a VI value of around about 114. And I think for this type of equipment that this fluid was designed for, the use of VI improvers was probably not realistic because of the high shear stresses involved in these systems. You'll see that the industrial hydraulic fluid has, great low temperature properties, low pull point, good pumping viscosity of -30 degrees C. And it has an air release time on their technical data sheet of less than 4. I actually consider that value to be quite high for an ISO 46 viscosity grade. It is an improvement versus previous generations of this type of fluid. But nonetheless, I think a value of 4 is, if it is 4, is quite high. It does have a very good TOST life here of greater than 5,000 hours. And finally, we believe that this product is based on a ZDDP anti-wear package. We've looked at the ICP measurements, the zinc and the phosphorus content, and you can see that they're around about 90 and 73 ppm. On the right-hand side, you can see the data for the VBASE product. So we have a VI of 174. This product doesn't contain any VI improvers. Has very good low temperature properties, so pull point of -42, etc. But what is quite remarkable about this product is that it does have a very, very low air release time of 0.1 minutes. And we think that it has a lot of value in the industry, simply because if you're an equipment builder, you're looking to build smaller sump reservoirs, reduce your capital costs, you will need to have fluids that offer superior air release characteristics versus, conventional products. In my experience, products which typically have fast air release often have foaming issues. But when we've looked at the VBASE technology and the foaming performance in the ASTM D892 test method, we see no foaming at all with this type of product. It does have a lower TOS life, a little bit lower than many other fluids that we've developed. We've been seeing values of typically around about 8,000 hours under the dry TOS conditions. This one is a little bit lower and certainly lower than the industrial hydraulic fluid. And right at the bottom and the right-hand side there, you can see that this product is based on, ashless anti-wear technology. So I'd like to share with you some of the data that Paul and his team has generated here. What we're looking at here on this chart are the motor torque loss reductions at a series of different motor speeds and pressures. I need to explain this quite carefully. When I first looked at this chart here, I was trying to get my head around it, but particularly with regards to the x-axis. So on the y-axis, we have the motor torque loss, and we need that number to be as low as possible. And on the x-axis, we simply have the different motor speeds. But at certain motor speeds, we use 3 different types of pressures, which I've tried to highlight there in the boxes on the x-axis. So Paul has run these at at 3,988 psi, 4,350 psi, and 4,712 psi. If you look at the the graph here very carefully, you see it very much resembles a Strybeck curve to me. So at low speed, you're in the boundary region. As you move to higher speeds, it appears that you're moving more towards the mixed DHD region, and then towards the very high speed range, you're moving into the hydrodynamic region. What you very clearly see here with the green dots, which are the VBASE products, versus the red squares, which are the industrial hydraulic fluid, are significantly lower motor torque losses for the VBASE product, particularly at the low speeds. And at the low speeds, this is where the equipment is really under a lot of load and doing its main work. So looking at this a little bit further, Paul and his team have also looked at system flow loss reduction. And again, on the x-axis, we see the motor speed at certain pressures, and on the y-axis, we see the system flow loss again. And across that entire range of speeds, what we see is that the VBASE product in green versus the industrial product in red shows, again, significantly lower flow losses. So that's consistent flow loss reduction across that full operating regime. That means that we've got potentially improved power transfer and ultimately increased productivity. And that might in turn lead to greater component reliability. Now, this goes into a summary in some way, shape, or form of the data that we've just looked at. And my colleague, Zach, has put this nice chart together. I mentioned before that efficiency is important in our industry, but perhaps to the end users, productivity of the equipment, which is really, really important. And so what Zach has done here is looked at the VBASE data, and he's normalized that versus the industrial hydraulic fluid. At the top of your screen there, you can see the motor output power ratio. At the bottom of the screen in blue, you can see the pump input power ratio. And so we need the motor output ratio to be greater than 1. If it is, then we have higher productivity in that work zone. And you can actually see with the amber traces here that we deliver around about 25% more power output at the low speeds. And that's very, very significant compared to the industry standard product. Also, with regards to the blue dots here, the pump input ratio preferentially needs to be less than 1. If we have that, then we have more flow available to do the work. So we've been really delighted with the data that has been generated on our fluid versus that industry standard product. So when we look at a summary of that hydraulic efficiency test data, then what we can see is that the VBASE secondary polyester technology does allow machines to potentially deliver more power, particularly to the tool, and also consume less power at the pump. And we know from a productivity point of view as well that the reduction of torque and flow losses, of course, translates into, for example, more tons moved per hour, less fuel burned per ton, and indeed potentially longer component life. Now, what is important to those equipment users is really the total cost of ownership, and as well as having improved machine productivity, then the need to have longer fluid life, longer component lifetime is also very important. And what we're doing in our company is we're in the process of, at the moment, of generating more equipment data, looking at wear performance and component life and so on and so forth versus industry standards for this fluid. So again, I'll just pause there and ask if there are any questions on the hydraulic efficiency testing.
Hi, yeah, I think we had. This one seems like it was answered. There's one from Patrick that says, can you tell us more about the density behavior or expansion coefficient with delta T. Speaking of thermal management, can you expand on the thermal conductivity?
Yeah, I may bring in my colleague here, Zach Hunt, who's been very familiar with the actual testing. From a thermal conductivity point of view, what I can tell you is that the values that we've seen for the secondary polyester technology tend to be a little bit higher than the conventional hydrocarbon oils. So that kind of is a starting point. In terms of the expansion coefficients and so on, I don't recall us actually measuring that, but I'm going to defer that question to my colleague, Zach, who's on the line, who might be able to add to my answer.
Sorry, I was trying to find the microphone. Generally, for the thermal conductivity versus, group 2 through 4 oils, we've seen about 5 to 10% higher thermal conductivity with the VBASE secondary polyol ester base oils. When you look at esters and PAGs of the same viscosity, you're looking at roughly similar values. And again, I think a lot of this goes back to, as Martin stated earlier, that inbuilt oxygen content in all of those materials. And he's correct. For thermal expansion, we have not explicitly looked at that, but that is something that is on our agenda to investigate.
Yeah, thanks, Zach, for that.
We have another question. It says, have you compared the volumetric heat capacity with the polyalkylenic oil, polyalkylenic oil?
With the polyalkylene glycol oil?
Correct.
Martin, we had answered that in the chat, just FYI. We had said that, we did compare against PAGs, and the VBASE fluids for comparable viscosity grades are marginally higher, so about 3 to 7%, depending on the specific viscosity grade.
Sorry, I didn't see your response. You're right. We do have a question that just came in. Just curious to know if any efficiency productivity studies were done with a high VI mineral oil versus the VBASE product. I ask this since the hydraulic oil efficiency productivity improvement is primarily a function of the VI oil, which can be achieved using VI improvers.
Yeah, again, I'm going to defer that question to Zach because there were a whole series of fluid chemistries in this program. Zach, would you like to take on that question?
Sure, I'll take it. No, we did not look explicitly at a high VI mineral oil for this particular study. There are studies that I think are currently being published out of MSOE that investigate that activity. Those aren't our studies, so I don't feel free to speak on those. So feel free to reach out to MSOE on that front. The caution I would present in looking at the use of VI improvers to get to this point is that this is going to be shear in the system is greatly going to impact those results. So over time, those VI improvers are going to break down, and you will inherently lose any of that performance that you may see, fresh out of the gate.
Thanks, Zach. Okay, we'll go on to talk about a case study on a hydro-turbine oil. And as Stephen mentioned earlier on, the genesis of our whole business goes back to a grant that the Tetramer team, the mother company of VBASE, secured in order to formulate a hydro-turbine oil as part of a Department of Energy grant. And so the team developed that hydro-turbine fluid, and they did that by designing the secondary polyester chemistry. And since that point in time, I've taken that development further to generate some equipment data. And I'd like to share that with you, and particularly share data on the condition monitoring of that fluid in the field. To put a face on this fluid, so this product is called VBASE hydro-turbine oil, TEL. It has a viscosity of approximately 58 centistokes at 40 degrees C, so it falls between an ISO 46 and an ISO 68. It has a VI of 182, so very high. Its pull point is minus 18 degrees C, as you can see there, so a little bit higher than some of our other lower viscosity products. We had a question before on RPVOT values, and you can see here for this fluid we have a value of 1240 minutes, so it's got good oxidation stability per that test method. But it also has a very good dry tossed result here of about 8,000 hours. And I mentioned before that you can formulate products based on the secondary polyester chemistry to have very, very good oxidation performance. If you go a little bit further down that table there, you see the demulsibility result, which is very respectable. There's no issues with foaming, and of course it passes an FZG test at stage gate 12 plus. This product again is readily biodegradable with a high biocarbon content. Now, in order to secure a significant field trial, we had to go to GE in Switzerland and run this product on a combined thrust guide bearing test rig. And so they ran this at different speeds from 400 to 800 RPM with applied loads up to 13 megapascals. And really what they were looking for in this test was trying to maintain a uniform hydrodynamic film so that the bearings and the runner surfaces are not damaged. Now, as part of that, of course, they managed to show that with this technology, but it's part of all that as well. Often they try to break the film by applying very severe loads onto the system there. They had trouble breaking the load, breaking the system through the high loads applied there. We don't quite understand that, but we rather feel it's probably related to the pressure viscosity coefficient of the fluid, which we intend to measure. So very good uniform hydrodynamic film, which then allowed us to then transition into a full field trial in Sweden. So our team put together the formulation, of course, and we ran a trial, or are running a trial at the hydroelectric power station in Sweden. So this is a large-scale installation of our VBASE hydro-TEL product. The product is in a U8 turbine there, and this is, of course, a joint collaboration between Andritz, GE Renewable Energy, and Vattenfall. The goal of this trial really was to demonstrate equipment reliability, but also to ensure that we had full fluid stability in full-scale service. So I'll share with you some data here. The product has been in the equipment for about 18 months now. We've got the first 12 months of data here. This is data that has been measured by Vattenfall, so they share that data with us from time to time. You look at the viscometrics in the table on the left there, you see that the product is very, very stable from a viscometric point of view, which we're kind of delighted for. We track the acid number, of course, and there was a blip up on the acid number after 6 months. That seems to have stabilized after 12 months. We're quite interested in what the 18-month data point will tell us on that. The water content in that equipment varies between, as you can see there, 500 ppm and 1200 ppm. I rather feel that's seasonal. The demulsibility of the product, again, back to the question we had earlier on demulsibility, is excellent on this product. And again, the air release time, as you can see, is less than 2, so showing very fast air release here. Interestingly, if you look at the particle class here, the fluid seems to be getting cleaner over the trial period. And this might come back to the fact that, we have this inbuilt detergency within the fluid, helping not only the fluid to stay clean, but also the equipment to stay clean. On the right-hand side, you can see we've tracked the ICP data, the metals analysis, and we didn't see any significant changes in the elemental analysis over that 12-month period, which suggests that there's no issues with, for example, corrosion occurring or wear metals forming during the trial. What is interesting, though, is the fact that the operators of this turbine have noted that there is a 10 degrees C lower temperature versus the previous product that was in that equipment, which was a hydrocarbon-based turbine oil. And this may come back again to the point I made earlier around the volumetric heat capacity, so the heat management capability of the secondary polyol ester technology versus the hydrocarbon oil technology. So we're going to be conducting many more trials over the coming years to really validate that the volumetric heat capacity does play a very important role in heat management of equipment. So I will pause there one more time and ask if anyone has any questions on the turbine oil trial.
It looks like we have a question here from Robert saying, any testing or case studies with hydrodynamic bearings?
No, not at this point, no.
Okay. This is a long one. So when we are using mineral or synthetic oil cleanliness testing is a major issue in the hydraulic fluid. Very difficult to measure the cleanliness of the particle count if the fluid is contaminated with dark color contaminants or water. What is your suggestion for this VBASE used oil cleanliness code testing and measurement?
Yeah, we've simplistically used the ISO 4406 test method for looking at cleanliness of oils. I think that's, you know, an industry standard test method, but nothing beyond that.
Okay, I think you answered the second part is what ISO, NAS, ASTM, DIN method can you use to determine if the fluid is contaminated with other fluids or contaminants?
Yeah, I think if you were to do a forensic analysis of the oil, we would probably use you know, more sophisticated spectroscopic and chromatography techniques to look at any contamination. We'd also look at, for example, you know, using ICP, as I mentioned earlier, for looking at elemental analysis as well.
Okay. And then how will you check the miscibility compatibility test with other oils or machineries? What type recommended? What standard will we follow in the lab?
Yeah, we've simply looked at the compatibility of a wide range of different products at different ratios, of course. And I think that's always important to do, to look at what was in the equipment before and what you're replacing it with. So very simplistically looking at, you know, the compatibility at ambient temperature and higher temperatures as well. Nothing so scientific about the approach we use.
And then normally when using hydraulic oil, coolant, or in ships, seawater likely contaminate with hydraulic fluids. How would VBASE purified if high water or debris or unknown pollutants cross-contaminated?
Yeah, I didn't quite catch the last part of that question, but I think the question was about water contamination, was it?
Yeah, I'll reread it. Let me get my microphone, make sure I'm there. Normally when using hydraulic oil, coolant, or in ships, seawater likely to contaminate with hydraulic fluids, how would VBASE purified high water or debris or unknown pollutants cross-contaminate?
Well, first of all, on the water contamination issue, a really important point that perhaps I've overlooked is that these products, because they have this oxygen-rich backbone, can tolerate more water than a hydrocarbon oil. So very simplistically, the water is hydrogen bonded to the oligomer part of the molecules, so the ether bonds within the molecules. So that's good. So you can typically run with, I would say, probably up to about 5,000 ppm of water contamination in these fluids. If there's larger amounts of water in the fluids, I don't think we've addressed that in our company, but I would imagine some form of distillation would be, you know, the approach we would use.
Great, thank you. And then we have one last for right now. It says, have you looked at the traction coefficient of the VBASE oil versus the ISOVG 68 oil referred to? That might explain the lower viscous drag and lower temperatures.
Yeah, so we've been looking at traction coefficients using a mini traction machine. We did some work earlier on the lower viscosity grades. The traction coefficients from memory, typically at, for example, 70 newtons or 1.25 gigapascals contact pressure on a steel ball, steel disc arrangement. So the industry standard kind of method there. We're looking at traction coefficients that are lower than hydrocarbon oils and fairly similar to some esters that we see in the industry. Perhaps not as low as some other technologies that we're aware of, but certainly lower than the hydrocarbon-based base oils.
Okay, looks like that's it for now. So you guys can go ahead.
Okay, we are pretty close to the end now, but I'm going to turn it back to Stephen to talk about a couple of things.
Thanks, Martin. Great job on that. And thanks everybody for your engagement and the questions. Hopefully we have a few more minutes left to address any further ones. But I wanted to address a few other things in terms of the commercial supply availability for these materials. And so first and foremost is manufacturing and supply reliability. So currently we have a robust toll manufacturing network in the United States, and we have several partners that are qualified to make sure that we have security of supply. We know that that's a concern in the last several years has been a big concern for the industry. And so making sure that we both have multiple approved raw materials for every raw material we use and multiple production sites and inventory positions to be able to make sure that we are a reliable and robust partner is a key pillar of what we're doing here. So we do have several partners secured. We are able to go anywhere from packaged goods up to bulk in the kilotons or have no concerns from a capacity standpoint, and are working to expand geographically to support growth in the further regions in the near future. So actively engage with partners in the EU as an example, as that market starts to open up, as REACH certification comes to fruition. So very robust supply chain, raw material positions. Anybody that can make an ester typically can make our esters. And so those that have contract manufacturing models, those are the partners we rely on to make sure that we serve our customer base in the right way going forward. Then as far as how to learn more, I saw that there was a question in the chat regarding this. So we do have a dedicated email address, samples@vbaseoil.com, where we can take requests for that. I encourage you to go to our website, vbaseoil.com, because it is quite extensive, has a lot of the data that Martin has been showing and referencing, a lot of the product specific data, applications where we think our products fit best in, those recommendations, case studies, sustainability goals, and then all of these efforts that we're doing with regards to podcasts, articles, and news. And there is an online sample request form there as well. And or if you reach out to Martin and I, which will share our contact details, we can happily assist you with that as well.
Yeah, thanks, Stephen.
Martin, to conclude for us.
Yeah, if I can just conclude presentation here. So this chemistry is new to our industry. These are oxygen-rich hybrid base oils. They have a lot of the environmental and functional performance of esters and the functional performance of PAGs. As we mentioned earlier, this is a platform technology, so we can bend the molecules lots of different ways to get the optimum functional performance. And our research team will be continuing to optimize the technology for the tribology challenges of today and tomorrow. I mentioned these products have really interesting thermal management properties, particularly the volumetric heat capacities. That can, of course, help with solving some of the heat management issues in our industry. Of course, we talked about equipment efficiency and productivity through the case studies that we talked about. And finally, I would say that these are really high performance, sustainable synthetic base oils. So not only delivering high functional performance, but also they have the icing on the cake from the point of view that they have very good environmental performance benefits as well. Stephen and I, and of course our entire VBASE team, we are very thankful and grateful for your attendance today. Please contact us with any questions or, any need for any further information. I hope you've enjoyed the webinar today, and we would be, and we look forward to engagement with you, of course, in the near future. So
I'd
I
also
think
like to add my thanks as well to the audience here. It's been a really engaging conversation. Hopefully, this is just the start of future endeavors here, and we're happy to dive deeper into any of these topics based on the feedback from the team here.
Guys, I know we did have a question. Somebody just emailed me about, is this video going to be put up somewhere, or is there anywhere where they can find the recording of it after I hand it off to you later on today?
I think the answer to that is probably yes. I mean, we'll talk with our team internally to see whether, you know, we can do that.
Absolutely.
Did you guys want to take any questions if anybody wanted to unmute themselves or put them in the chat, or do you guys, it's up to you.
Absolutely. We have the last 3 minutes. If anyone has a question
Sure.
they'd like to come and speak to us, we're happy to take it. There was one additional one in the chat, Martin, if we want to address it. It says, VBASE oil, we see high TAN for used oil. What is the caution and action limits used for used VBASE oil, which needs to be replaced?
Stephen, can you repeat that? I'm sorry, but it cut out a little bit.
No problem. There's a comment that says VBASE oils, we see high TAN for the used oil. What is the caution and action limits for the used VBASE oil, which needs to be replaced?
That's a very good question, and I think you know, I would answer that question. Typically, for this technology, we would look at monitoring the fluid and you know, throughout its life. Once the TAN value is above 1 from its starting value, then I think it's time to watch the fluid very carefully. Once it gets to around about 2 above its starting value, then you need to think about replacing the fluid. However, a key point on this is that you think about the degradation products of some esters. For example, some of the oleate-based esters. The oleate-based esters are derived from what I would call weak acids. Oleic acid is a weak acid compared to, say, a C5 valeric acid. So with regards to the aging of the fluid, for those type of esters which use weak acids, then I would say that the TAN value increase can be much higher than perhaps if you're using a shorter chain acid in the system that's, of course, stronger. So I hope that gives some kind of direction.
Thanks, Martin.
We had another question. Are there plans to obtain FM 6930 approval for VBASES hydraulic fluids? If so, what's the time frame?
Great question as well. So there are companies, you know, in North America that are looking at the FM approval, the 6930. We've been thinking about that ourselves. You know, should we demonstrate that we can meet that standard with our technology? Of course, it does require a lot of resources and big commitment financially to do that. So, like I say, I think the message I'd like to leave you with is that there are companies engaged with FM, looking at the FM approvals for this type of technology.
And Sean, feel free to reach out to myself or Martin to talk a little bit more, because if there is an interest in a rebrand, one of our channels to market is to look at that as a finished solution for you. We're not interested in selling VBASE products to end users in terms of a formulated lubricant, but if you're looking to do a rebrand off of ours and sell it with your brand name, that's something we would consider. So please reach out to Martin or myself, and we're happy to talk a little further. Over to you, Robert.
All right, guys. Thank you so much for your time today. Thanks everybody for attending. We appreciate it. We will obviously follow up with you if VBASE does decide to publish the webinar. Otherwise, thank you for your time today. Thanks for your participation, and we hope you have a good rest of your day.
Thanks for moderating as well, and you did a great job.
No problem. Thanks, guys.
Thanks, Robert. Thanks, everyone. Bye-bye.
Thank you. Thank you so much.